All right, guys. Yes. Then move. Yes. All right. So, start chapter 10 today. Chapter 10 is all about areas. Chapter 11 is all about taking those area formulas that we learned here and transferring them to volumes. Okay? So, what we learn here is ultimately the foundation for 2 chapters. Okay? What stinks about this chapter that students struggle with is that we're going to do a lot of conversions. Okay? Square feet to square inches to square miles. Okay? That kind of thing. Okay? What also stinks about this chapter that people struggle with is that there are a lot, and I mean a lot, of questions that play on your knowledge of things from chapter 5, things from chapter 4, things from chapter 6, things from chapter 7. And if you don't have the ability to remember those things, or the ability to know that we've seen it, and know that you have information written somewhere or resources somewhere to go back to and refresh on, you're going to struggle. Okay? So I just want to open your eyes to that first. Okay? This is beginning of the year, I told you at some point there's going to be some chapters that are kind of the culmination of the entire year. Chapters 10 and 11 are that culmination. Okay? Chapter 12 talks about circles. Chapter 13 is probability. Chapter 13 comes back, kind of uses the whole chapter or the whole textbook as well. But we're getting to that point where we're going to use, 7-8 months worth of information on one chapter. Okay? Yes. We will do surface area. That'll be in the next chapter. Okay? Okay, so we have some postulates to identify, and I think maybe one of the first things to talk about as well is the area form or area definition. Okay? Okay? So area, kind of maybe a rough definition, is the square region or the region, usually in square units, that a 2D shape or two-dimensional shape encloses. Okay? That is what area is going to be defined as. Okay? If you remember back to, I don't know, 5th or 6th grade when you guys started first kind of introducing the idea of area, they gave you, graph paper. And you had a picture drawn on that graph paper, and they asked you, go count how many 1-by-1 blocks are enclosed by that shape, right? Okay, and that was annoying. It was a pain in the butt. But what you were doing was adding up the square units that shape enclosed, right? Does that make sense? Okay. And, sometimes you had to, estimate, chop up blocks, that kind of thing, right? Okay, but you were trying to get familiar with what the definition of area is. Okay? We have some postulates here. The area of a square is the length of a side times the length of a side. Okay? So we square that, side times side, so it's side squared, right? Okay? The reason we talk about that area formula first is because then every other shape we talk about can be made up by chunking it up into little squares that are S by S or 1-by-1 or whatever. Okay? We're going to break our other areas up into square units. Okay? The final statement there is that if two figures are congruent, they have the same area. If they're congruent, then their dimensions are all the same, right? Lengths, width, height, altitudes, all that kind of stuff, they're all the same. Okay? Therefore, when I pick them off and put them in a formula for a shape that is congruent to another shape they've already found the area for, then the components inside my formulas have to be the same. Therefore, my areas are going to be the same, right? Okay? If I had two squares up there that both had side lengths of S, and you used S squared for a formula on both of them, you're going to get the same formula back. Okay? So that's kind of the foundation of what we mean by area and the tools that we're going to use to determine area. Okay? Now, there are a couple segments that are very important for us when we talk about area and talk about the different formulas that we're going to generate today and tomorrow and the next couple days, okay? And that segment is an altitude. And we've talked about this a lot with triangles. Let me show you an altitude of a triangle real quick. Make sure we remember what it is. By definition, okay, the altitude of a triangle goes from a vertex of a triangle. It doesn't matter which vertex, okay? So you got three of these. But it goes from maybe A perpendicular to the opposite side. So if you remember, that distance, A to D, is considered a altitude. That distance right there is an altitude. Does that make sense to everybody? Perpendicular here. Okay, we call that H in a lot of our formulas. Okay. Now, as I change the triangle, that altitude now disappeared, right? Okay. Now the reason it disappeared is because it's on the outside of the triangle here. So I haven't created this well enough to get to show up. So let me extend this segment as a ray. And now perpendicular there to there. So all right, so that would be an altitude of an obtuse triangle. Does that make sense to everybody? Okay. So there it works its way back inside. There it's now on the outside. If I were to view, maybe let's just put a line here for, like, let's say that line right there is my desk, or it's your, just your horizontal. Okay. Would you guys all agree that that black line, measuring from the top straight down, that makes sense that would be an altitude, right, or a height, correct? Okay. It goes from a vertex perpendicular to the opposite side. Now, if it's an obtuse triangle, I can't go perpendicular from A to the interior of BC. No angle in there from A to BC. No line will create a 90-degree angle. So we have to go straight down to the desk. But that distance right there is still H, right? Okay. So we can do that from every vertex, A, B, or C, to the opposite side, and that's an altitude of a triangle. Now, just in general, an altitude for a quadrilateral is the same concept. You don't have to start at a vertex. Often it's useful to, okay? But you start with a point on one side, okay? And then you go perpendicular to the line containing the opposite side, or the opposite base. Okay, that's what that definition is saying. Start with a point on a base, and then you go perpendicular to the line containing the opposite side, or a lot of times it's called the opposite base. Yes, basically what we're looking at here is saying that it's the perpendicular line connecting two bases. Does that make sense? The perpendicular line connecting two bases. Now, that's for a quadrant. If we're going to go with that phrasing, that's for a quadrilateral, because that doesn't make a whole lot of sense saying it for triangles. Okay? Because triangles don't have two bases that you can connect with the perpendicular line. Okay? It's impossible. Take any two segments of a triangle and try to connect them with a right angle, or a perpendicular line, so it's perpendicular to both of them. You can't do it.
Could that be like not just for a quadrilateral, but could it be for like anything other than a triangle? Like if it's an octagon.
Well, when we start finding areas of octagons, we won't necessarily talk about going all the way through the shape. Usually, for an octagon, all we have to do to find the area is we deal with the center of the octagon straight down to a side. Basically, yeah, for side figure, this is what we're interested in regards to altitude. Okay, so each one of those, let's look at the trapezoid first. The trapezoid's not usually a difficult one. Because by definition, we know that's the base and that's the base, right? In a trapezoid, we have said that the parallel sides are always bases. So then it's easy to see any line that's connecting those perpendicularly is a altitude, right? Okay, so those dotted lines are all altitudes. Now, the reason we say that is because, there's going to be times where your trapezoid is like that, where if I'm using the bottom of my screen as kind of my desk or whatever, that trapezoid, you see that your altitude is not just a vertical distance, right? Those dotted lines are still altitudes. They're still h. Okay? And what I think is problematic for people is that when they see h, they think it's got to be vertical. It doesn't. Okay? Think about your height. How tall are you? Think about how tall you are right now. Okay? When you lay down, are you still the same tallness? Mm-hmm. Yeah. Okay? You still have the same height whether you're standing or laying down, right? Okay? Now, the same thing happens for other shapes. Okay? But other shapes, so the trapezoid, because those are my only bases, those are my only altitudes. So look at the parallelogram. Okay? The parallelogram, the way I've got it set up here, that's my base, and that's my base. So the dotted lines then are the perpendicular lines connecting opposite bases, right? Okay? Well, can't I take that parallelogram and do this with it? Actually, let's do it this way. Okay, so it's kind of resting. So at the bottom of my slide here is my table. Okay, those would still be altitudes, right? Do you agree with that? But would most of you, if that was, if this gray thing down here was your desk or your tabletop or whatever, and you had a tape measure, and this thing was, you guys remember canograms? They were like red, yellow, blue, little plastic parallelograms and trapezoids, stuff like that you put together in, okay, those are tanograms. So if you had like a tanogram in front of you and you put it on your desk, most of you would take your ruler or your tape measure and measure straight down to the top of your desk, right? Does that make sense? Is that solid red segment also an altitude? Absolutely. Because it goes from a base perpendicular to the opposite side. Yes?
How is the one in the middle of the trapezoid an altitude? If it's not from a point?
If it's not what?
From a thing.
It doesn't have to it doesn't have to be from a vertex. It just to be a altitude over here, they just have to be perpendicular to both bases. So this is an altitude. Would that be an altitude? Yeah, it goes from that base perpendicular to the opposite base, right? Okay. Now look at that figure on the left. Would you make the argument that the red distances are probably different than the black dotted distances? Yeah. Yes. Okay. But regardless of which ones I use, I should get the appropriate area for these things when we see our formulas here in a moment. Okay. What I need you to understand is that for triangles, you have 3 different altitudes. And unless it's an equilateral triangle, those 3 altitudes are different. Okay? If it's an isosceles triangle, 2 of the 3 are the same. 1 of them is different. And any other triangle, they are always 3 different altitudes. So you guys know the area formula for a triangle, right? 1/2 BH, right? Okay? Well, that H has 3 different values that it could take on. That B has 3 different values that it could take on, okay, because of what B and H represent in a triangle. When we deal with the altitude for a parallelogram, let's talk about the area of the parallelogram here in a little bit, okay? It can take on 2 values. It can take on that dotted segment, or it can take on that red segment, okay? When we talk about it in trapezoids later in this chapter, it can only take on that dotted segment here. That's the only altitude for a trapezoid, okay? All right, so you guys know this. Area of a rectangle Base times height, right? Now, what's another formula you've probably learned in the past? Length times width, right? So what I think is interesting about mathematics is that somebody has sat down and they have kind of reworked the dynamics of all of mathematics and realized that when I come up with the area formula for a triangle, it is based off the area formula for a rectangle. So then that tells me how I should probably use variables to represent the area of a rectangle. For this mere fact, when we talk about the area of a triangle, it's 1/2 BH, right? The BH is coming from a rectangle. Okay, I'll talk about why here in a little bit. It makes sense then because every triangle has a B and an H. Every triangle has a base and a height, right? If I were to use L and W here, if those were the choices I used to define my variables, I'd have areas length times width, right? But then if I build my triangle formula off that, it'd be 1/2 length times width. Well then, in a triangle, does the triangle have a length? And a triangle have a width? No, but it had a base and a height, right? Does that make sense? Okay? So the defining of variables is key here. It's critical. And a lot of people want to fight against that urge to say, well, I know it's L times W. That's fine. Use it if you like that. But in order to see the relationships that exist throughout other formulas, BH is what we're going to use. Okay? So B and H. Okay? Base and H is the altitude. Okay? Now, and I cut and paste these straight out of textbooks. Okay? And they use height for H, which is not wrong, but I don't think it's the best thing to use. Because again, what's the distance that you think about when you see height? You think up and down, right? Doesn't have to be. Okay? Doesn't have to be an up and down distance. It does have to be constructed with perpendicular lines, though.
What would you call it?
Altitude. I'd still use the variable H, but I would refer to it, instead of calling it height, I would refer to it as altitude. So base times altitude. All right. Area of so you know the area of a rectangle, B times H. Area of a parallelogram, B times H. Okay? Now, why is the area of a rectangle B times H and the area of a parallelogram B times H?
A parallelogram is kind of a slanted rectangle.
Okay, so a parallelogram, we got that slanted rectangle. So what my argument here is, I was hoping that we can discuss the idea that, you know, if a rectangle, well, let's phrase it this way, if a parallelogram was a rectangle, then it would make sense of why it's B times H, right? If a parallelogram was a rectangle, it makes sense that it would be B times H, right? If you were a sophomore, it would make sense that you have, you know, X amount of credits, whatever you need for it to be a sophomore, right? Okay? But a parallelogram is not a rectangle, right? Okay? So that logic maybe doesn't make a whole lot of sense. The reason it's B times H is kind of what Kenny was saying, is that it's a slanted rectangle, okay? But let's think about just redistributing some areas here, okay? Now we're going to do, and this is why Chapter 9 came first, we're going to do some translations here, okay? Might do some rotations, might do some reflections, that kind of stuff. But when I do a translation, a reflection, or a rotation, do distances change? No, okay? So if the distances don't change, then the areas can't change either. Does that make sense to everybody? Okay? So we talked about isometries being things in which distances are preserved. Therefore, in an isometry, your image and preimage are congruent, right? So if shapes are congruent, the image and a preimage in transformations and in isometries have to have the same areas, right? So I want to keep that in mind as we go through this. Would you guys make the argument, or would you agree with me that if this is an altitude, if that's 5, and that's an altitude, that altitude could also be drawn from here, perpendicular to the line containing the opposite side? So I could draw that altitude right there, right? Okay. Now, what would you say about this segment here in comparison to that segment there? They're congruent. They're parallel and congruent. Why are they congruent? It's a theorem. what do those come from? What shape do those two sides come from?
They're both transversals that are the same angle on the same parallel line.
What shape is that blue shape? Parallelogram. What do you know about opposite sides of a parallelogram? They're congruent. Okay? So that's what I was saying about this chapter, is that there are relationships that exist that came from chapter 6, that came from chapter 4, came from chapter 5, that we have to be able to regurgitate, okay, to be able to use. Or wash them off after you regurgitate them. So that's 5, right? Okay. So we now have, obviously you told me that the opposite sides are congruent. Okay, so you got that distance congruent to that distance. Are these 5s the same? Yes. Okay. What's that telling me right now about those two triangles? Why? I don't necessarily know that it'd be kind of hard to determine whether that angle, it's probably doable, whether that angle is the same as that one. Okay, so you got side-side angle, and if we reverse that, it's not as friendly, right? But what kind of triangle is it? The right triangle. So side-side angle does work in right triangles, but we call it what? What is this side here for in a right triangle? Hypotenuse, and what's that side? A leg. So what do we call it? Why are they congruent? Hypotenuse leg theorem, right? Okay, which is the side-side angle postulate or theorem in right triangles. So those two triangles are congruent. Why is that nice to know? If this triangle is congruent to that one, what's it tell me about their areas? They're the same. So can't I do something like this? Chop it off here and reattach it here. And then when I reattach it there, what shape did I just make? A rectangle. What's the area formula for a rectangle? Base times height, right? Is this my height? Is this my base? Yeah, and those two distances were not altered at all in this process, right? Okay, so I redistributed area, correct? I took this blue triangle off here, cut it off, redistributed over here, taped it back on, glued it back on, whatever you want to say, and it created that rectangle, right? And we know the area formula for a rectangle is base times height, right? So if that thing was base times height, go back to the original, should be base times height as a parallelogram, this being H, this being B. So what's my area here? 60. Now we don't know the units, so we say units squared. Is that something we can do?
Yes.
All right. So that redistributing of areas to find a formula is very common in a lot of our formulas, a lot of our area, surface area, volume formulas. What I need you guys to understand with parallelograms is that parallelogram right there, if I were to ask you to draw in your altitude, I would argue that I would argue that 90% of you, if not more, would probably draw that altitude. Is that the altitude most of us are thinking? Yeah. Okay. Or, that blue one kind of moved left or right anywhere through that. You go from D prime down to maybe here. So that one, maybe you draw that one in, or maybe you draw this one in. But you would draw one in that's probably equivalent or congruent to that blue one, right? If I draw that one in, that would be the base, right? Yeah. Does that make sense to everybody? So L and M. So let's see here. If I were to take L times M, it gives me that area of 17.55. That's base times height, right? The area of that parallelogram is now 17.55. If I ask GeoGebra, it's actually got a tool here that says area. All I got to do is click on my area, and you see it is 17.55. So that is working, right? Okay. Now, what if I did something like this? What if I rotated, and you saw something like that? Okay. If I was looking at this one, I think most people would probably put in that altitude. Would that be an argument that would be safe to say? Okay, is that altitude there, that purple distance, different than the blue one previously? Yeah, the blue one down there on the left hand is 3.51, right? The purple one's 4.12. So there is the purple one grew, right? Okay, now what would be the base of that purple one? The base that goes with it would be this one, right? Okay, well, how does that relate to the other base of 5? It got smaller, right? So the altitude got bigger, but the base got smaller, right? That's an inverse relationship, correct? Okay. If I multiply those two things together, all I did here was a rotation, right? So it's a rigid motion. So those two figures, those two parallelograms, should still be the same, right? Should be the same area. So I take P times Q. That's the purple times the orange. Give me 17.55 again. Okay. Now here's the thing. This is the purpose I want to show this. I'm going to go back and put this on top of there. If I were to ask you to find out or give me a B and an H for this thing, are many of us going to give us the purple one and the orange one? No. But are they wrong? No. Okay. So those are viable options. When you work in your homework's going to give a question kind of like this. Let me kind of extend this a little bit.
I'm going to have to rotate it.
Okay, so your homework, guys, is going to do something like this. Now, I'm just going to put some random values in here. But they're going to tell you that maybe this distance here is 5. Maybe this distance here is 10. And maybe this distance here is 4. And they want you to come up with the distance of the purple. Okay? Now, and they might extend this out so they got a dotted line here. Okay? But let's think about the parallelogram. The 5 is a what for the parallelogram? An altitude. So 5 would be H, right? What would be B in this case if I'm using that 5? It'd be 10, right? It'd be this distance right here. B is the base, but it's the base is dictated by the side that the altitude is drawn to. So you get the area of that parallelogram to be 50, right? Okay. Well, this is, if we rotate it, going off of that image that I showed you previously, if I rotate it and let this side right here kind of be your desk, couldn't this also be an altitude? And what would be the base then? 4, right? Because it's the side that the base, the base is the side that the altitude is drawn to. So then I'd have B times H being 4 times H. And they want me to find H. A was 50, previously found by using the equation with the other information, right? So can I solve that and get H to be 12.5? Okay. So what they're going to ask you, and the whole purpose of this question is to target your understanding of the fact that there are 2 altitudes for a parallelogram. And they're probably different, okay? Therefore, the bases that they're associated with are different. But when I multiply them together, a base times a height, and then a second base times a second height, in the same parallelogram, I should still get the same areas back. Is that all right? So you'll see that question. If we have to talk about it tomorrow, we can. Let's just do a real quick one just to kind of talk about these two. What are you going to use as your altitude in that first picture? 4. What is in the base? 5. So 4 times 5 is 20, right? 20 inches squared. Okay? What's that 4.5's purpose? To trick you. Okay? 7th grade, 8th grade, 9th grade, they gave you formulas B and H. You know you need 2 things. And then in the pictures, they gave you 2 things, right? Here, they're going to give you extra things to confuse you. Okay? They may even give you, say you need 2 values. they'll give you one that you need, so they might give you B, and then they give you two other values that you don't need for your formula, but you need in order to find the H for your formula. Does that make sense? We'll do an example of that here in a little bit. So you're going to have to do, it's kind of like playing a game. What are they giving me? And what are all the relationships that we've learned from chapter 1 to chapter 9 that's going to allow me to find the components of my formula? Okay. What about B there? What's your base going to be? Or maybe what's your altitude going to be? I think that's an easier question. 3.5, 3.5. Okay. So if that's my altitude, because it's perpendicular, right? That's the only distance up there that's perpendicular. What base does it go to? It goes to 2. So my altitude is 3.5, and my base is 2, so 7 centimeters squared. That's something we can do? All right. This is kind of what I was saying, that they're going to give you numbers that don't directly fit your formula, but you can manipulate the process, you can manipulate the picture using other concepts to find the things that you need for your formula. Hold on a second. So, in this case, the 12 and the 31, okay? You can't just multiply those together. Does everybody understand that? One of them is not a height, one of them is not a base, okay, depending on how you want to look at it. So what do you want, what would most people say that 31 is? 31 is the base, okay? So I need to find H, and I'm going to make the argument that this is H here, right? What do I have here?
You have like 45, 45, 90, 90.
Okay, so what is my hypotenuse in a 45, 45, 90? N radical 2. Okay, so we set that up. All right, if you remember, about 3, 4, 5 weeks ago when we were doing this, I told you there's going to be a point in the year where they just start popping up, and we just start working through them, and I'm not going to explain how to do them, because if I explain how to do every one of these guys, we're never going to get through anything. Okay? So if you struggle with 45, 45, 90, 30, 60, 90 still, or SOHCAHTOA, because that's going to exist as well, you need to go back to those resources. Go back to the classroom lectures that I've videotaped. Go back to the YouTube videos that I provide you with and relearn that stuff. Okay? Because if you don't, chapter 11 is going to be a nightmare. Chapter 10 is going to be a nightmare. Okay? Solve this by dividing by radical 2, right? So you get 12 divided by radical 2. I rationalize that. Get 12 root 2 over 2. What's that turn into? 6 root 2. Okay? So that's my H, right? So you have 31 times 6 root 2. And that turns into 186 root 2. Okay? And now it's unit squared, right? Okay? Now, somebody in the last class said, well, why can't I use SOHCAHTOA? You can. So they said, I need to find H. So they said, sine of 45 is equal to H over 12, right? So 12 sine of 45 is equal to H. Okay? So I can leave this as an exact answer, guys. I can still say the base is 31. The altitude is 12 times sine of 45. Now 31 times 10 is 310, right? And then I have 31 times 2, which is 62. So is that 372? Sine of 45. That's an exact answer. Okay? But in Math Excel and on your end of course exam, they might have the question stated as leave it in simplest radical form. Which one of these is simplest radical form? Simplest radical form. That one there, right? So sometimes the directions are going to dictate whether you're allowed to use SOHCAHTOA or not. Is that all right, everybody? Okay. Now, if it doesn't dictate, if it says rounds to the 10th place or 100th place, use either approach that you want. Okay. But if they're asking you to leave it as an exact value with radicals, you got to use special right triangles. Okay. Now, I hope nobody did this, but you could introduce an altitude here. That's 45. Okay. This would be my n radical 2 side, right? Okay? I could then say that's in and that's in. Okay? Let's just see if this works. Let's go. So I have 31 over root 2 is equal to n, right? Does that make sense, everybody? Now that would be my altitude. I guess, actually, can I do that? Yeah, I think I can do it. And this would be, so that would be 12, wouldn't it? Okay. This here would be n. So if that's my altitude, this would be my base, right? This 31 over root 2 times 12 end up giving me the same result. So if I go, I think we said that was 372 over root 2, right? Rationalize that, multiply by root 2 over root 2. 372 root 2 over 2. What's 372 divided by 2? 186. So it does work out using the other altitude and other base. Okay? I just don't think it's easy to see that other altitude and other base. Okay? All right, so in homework, guys, you might come across a question like this, okay? That's an irregular shape, meaning we don't have a formula for that. Does that make sense? Most of our shapes that we come across in nature are irregular, meaning that they don't have formulas. They're not normal, but they can be broken up into regular shapes. Does that make sense? Okay, now, the way that we break them up, a lot of times there's a right way and a wrong way, or a best way and a not-so-good way, okay? Breaking this overall trapezoid up as a rectangle and a triangle is the best way. How can I find that dotted distance right there? Pythagorean theorem, okay? 625 minus 49, okay, is going to equal 24 squared, okay? So this distance here is 24. Okay, so going through that Pythagorean theorem, I'm at the point now, guys, that should be something that we can do on our own. Convince yourself of that 24, you can go back and do it. Now can you find the area of that rectangle? 21 times 24, right? Whatever that equates to. Can you find the area of the triangle? Okay, what's the area of the triangle? Give me the formula. It'd be 1/2 what? What's your base going to be? 24, what's your height going to be? 7. Okay? So now that you have the area of your rectangle and you have the area of your triangle, what can you do with those two to find the shape, the area of the whole shape? Add them together. Okay? So you're going to see a lot of questions like that. We're not doing the questions that we've done in the past where it's just find the area of a triangle. Just find the area of the rectangle. Now, there are some of them, but most of them are building on top of those ideas. All right, why is the area of a triangle 1/2 BH? All right, so what I've created here is that is a rectangle. That is always going to be a rectangle. All 4 angles there are right angles. Okay? What do you know about the red triangle and the blue triangle? They're the same, okay? Opposite sides of a rectangle are congruent. And then this side, I think that's the easiest way to see it. That side's in both triangles, right? So those 2 triangles are congruent. So if this this area was A, and this area was A, you'd have 2 A's equaling the area of the rectangle, correct? So then one of those A's, if I divide both sides by 2, one of those A's is BH over 2, correct? Is that 1/2 BH? Yeah, okay. Now, that's just working with right triangles there. Does that same principle exist here? Okay, now I've already so normally we'd be looking at that blue triangle, find the area of that blue triangle. Well, that blue triangle comes from some rectangle, right? Every triangle you come across is going to come from some rectangle. If I draw in that line right there, is this blue triangle here the same as that green one? Okay, is this blue triangle here the same as that red one? So those triangles are congruent for the same rate side as what we saw in that first situation. Okay? So would you guys agree that if I took this green one and kind of rotated it and attached it to this blue one, or not blue, the red one or orange one, and rotate it so I can attach the green one and the orange one together, would they make up the blue one? Can you visualize that? Okay? So how many blue ones do you really have inside the original rectangle? You have 2. And because these 2 are congruent and these 2 are congruent, that means this blue one is congruent to the green one plus the red one, right? So then we still have essentially 2 triangles that are congruent inside that rectangle. So every single triangle you come across is half of some larger rectangle. Okay? Now, when we deal with triangles, you guys have done B times H for right triangles a lot. And it doesn't matter which side is B and which side is H in a right triangle. They're both legs. Okay? Be careful with that when you get to other triangles. Okay? H has to be an altitude, has to be a perpendicular distance. I want to do this question, and then we'll be done. Basically, it says that you've got a sail. You want to make it out of some fabric, and you need to know how much square footage you need. Okay, couple ways of doing this. Okay, area is 1/2 BH, correct? Okay, what's your base going to be here? 13 feet. I'm going to write it this way. Don't write it this way yet. 13 feet 4 inches, and your height would be 12 feet 2 inches. And the reason I'll write it this way is fourth period I asked 13 feet 4 inches as a decimal is, and I got what answer? I got 13.4 as the answer. Is that right? Why not? Okay, so it's not out of tens, right? Okay, if there were 10 inches in a foot, then absolutely, but not. Okay, it's 4 out of 12. So that's 0.33333333, right? Now, for my purposes in this question, I don't want to round anything. I don't want to go 0.33. I don't want to write that as 13.33333. Okay? So let's do this. You can do it this way. You go 13 feet and 4 twelfths, and you can multiply, change that mixed number to an improper fraction, right? But I think it's easier to do this. How many inches are there in a foot? 12. So how many inches are there in 13 feet? 156. Plus these 4 would be how much? 160. Okay. How many inches are there in 12 feet? 144 plus the 2? 146. Now, if you multiply those together and take half of it, you get this. Okay. Now, if this was a multiple choice question, option A is going to be that number. Are you right if you choose that option? No. Okay. You have the right amount. It's just in a different unit, right? Okay. So let's convert this. Okay. Now, if you remember anything from science, it's usually the response I get. I don't want inches in my answer, right? I want feet squared. Okay? Now, what does inches squared mean? Inches times inches, right? Okay? So if I want these to cancel out, what is the number one answer that I get when people say, or when I ask a question, how do I get inches squared into feet squared? What do they tell me to divide by? 24. Divide by 12. Okay? 24 is the next incorrect answer that I get. Okay? Because I put 12 here, and that's inches, right? Does that relate to 1 foot? That's the reason you want to say divide by 12, because you want to get rid of that inch, right? But now think about what happens here. This was inches times inches, and those are in the numerator, right? This is inches on the denominator. Well, doesn't only one of those cancel out? So now, unit-wise, if I was done there, unit-wise, I'd be left with inch feet. And that doesn't make any sense, right? So what do I need to do again? Go 1 foot over 12 inches again. Now that inch will cancel with the remaining one there. And now what are the only units you have left over? Feet times feet, which is feet squared. Okay? Now think about what this is doing. When I multiply by that conversion right there, it's taking this number here that was in inches, and it's putting it back into feet. Well, if I put that one back into feet, shouldn't I put that one back into feet? So that's what that one right there is doing. That makes sense? So when you convert, that's what you're doing. And then how we decide whether we cancel units and all that kind of stuff is actually taking your values that you use and converting them all back appropriately. Not just one or two of them, but all of them. So now you would really be dividing, instead of by 12, you divide by 144. Okay? And that turns out to be 81 1/9 square feet. Okay? If you do it on your calculator, you're going to see 81.11111. Does everybody know that if I have a point and then whatever number, it's that number over 9? It's like 0.555555 is 5/9. Okay? But your homework is going to be like that throughout the rest of the year, guys, for the most part, where we're using multiple concepts throughout the course from multiple chapters. There's going to be conversions. There's going to be some problem-solving skills, some logical thinking that needs to be taking place. Okay? So your homework is open. Due tomorrow. Hopefully go on to 10-2 tomorrow. Excuse me?